4 billion years ago, Mars had everything. A magnetic field, a thick atmosphere, liquid water running across its surface. Maybe, the conditions for something like life. Then its core cooled. The magnetic field collapsed. This solar wind spent the next 4 billion years quietly dismantling everything else, one particle at a time. What's left is a frozen, irradiated corpse where the soil contains a thyroid-destroying chemical at concentrations millions of times above what's considered safe on Earth. The dust storms there last months, with a single mission requiring 2.7 years with absolutely no possibility of rescue or return. Yet we're sending people there soon. People who can't come back early. People who will exceed NASA's lifetime radiation limit before the mission ends. If you've ever wondered what the first Mars mission actually is beneath the headlines, welcome. Stay with me as we explore the terrifying truth about the first mission to Mars. If you are new here, welcome to Interstellar Dreams. Subscribe and get comfortable, because by the end of this, that little red dot in the night sky will never look quite so innocent again. Now settle in and let's ease into it. Part 1. You don't come back from this. There is a number that NASA does not put in its press releases. It does not appear in the glossy mission concept art. It is not mentioned in the congressional funding hearings. And it is almost never brought up in the breathless news coverage every time a rocket test goes well or a rover sends back another postcard from the red planet. The number is 600 millisieverts. That is NASA's official career radiation limit for astronauts, the maximum cumulative dose a human being is allowed to receive across their entire professional life in space before the agency considers the health risk too high to justify further missions. 600 millisieverts, a career, a lifetime. And here is the thing that should make you stop whatever you're doing right now and actually think about this. A single round trip to Mars, depending on solar activity, will expose the crew to somewhere between 625 and 1650 millisieverts. Not over a career, on one mission. Before the crew even unpacks their equipment on the Martian surface, they will have already exceeded the limit that NASA considers acceptable for an entire human lifetime of spaceflight. The agency that defined that limit will be the same one sending people past it, knowingly, with no way to bring them back early if something goes wrong. That single fact tells you more about what the first Mars mission actually is than any amount of promotional material ever could. We have been sold a story about Mars for decades. It is a good story. It has heroes and destiny, and the poetic idea that humanity is a species that does not stay in one place. Elon Musk talks about a self-sustaining city of 1 million people. NASA talks about boot prints in the rust-coloured soil and the next giant leap. Science communicators, this channel included, talk about the wonder of another world. And none of that is dishonest exactly. Mars is real. The ambition is real. The science would be extraordinary. But there is a version of this story that almost nobody tells, and it is the version where you sit down and actually account for every single thing that has to go right for 4 or 5 human beings to survive 2 years and 7 months on a planet that is, in every measurable sense, incompatible with human biology. That is what this is. Not a celebration, not a debunking, something more uncomfortable than either of those things. This is a clear-eyed accounting of what the first mission to Mars actually requires, what it actually does to the human body, and why the people who eventually make that journey will not be explorers in any romantic sense of the word. They will be operators, managers of a fragile bubble of engineered survivability surrounded on all sides by a world that will kill them in seconds if that bubble fails. Every breath they take will be manufactured. Every sip of water will be recycled. Every calorie will have been launched from Earth years before they arrive. And if anything in that chain breaks, the pressurization, the power, the food supply, the medical equipment, there is no rescue mission coming. There is no abort. There is no version of events where someone on Earth pushes a button and brings them home early. The 2.7-year mission duration is not a scheduling inconvenience. It is the defining constraint from which every other risk multiplies. Think about what 2.7 years actually means in terms of human vulnerability. That is long enough for a previously undetected medical condition to become a crisis. Long enough for the psychological strain of total isolation to reshape how crew members relate to each other and to mission control. Long enough for a dust storm to last months and drain the power systems the crew depends on to stay warm and breathe. Long enough for the cumulative radiation to start affecting cognitive function in ways that might compromise the very decision-making the crew needs to survive. Duration does not just add risk, it compounds it. Every hazard you will hear about in the next 2 hours becomes more dangerous the longer the mission lasts, and the mission lasts longer than any human being has ever been this far from help. Mars is not just a hostile environment. Hostile implies it is indifferent to you, the way a mountain is indifferent to the climber. Mars is something closer to actively incompatible with the kind of creature you are. You are a warm, wet, pressurized organism that evolved over millions of years in a very specific set of conditions: a thick nitrogen-oxygen atmosphere, a strong magnetic field deflecting radiation, liquid water, a gravity close to what your cardiovascular system expects. Mars has almost none of those things. The atmospheric pressure at the Martian surface is roughly 610 pascals. Earth's is about 101,300 pascals. That is not a difference in degree. That is a difference in kind. The moment a Mars suit fails, you are not in a dangerous environment. You're in an immediately lethal one. So think of the crew not as astronauts in the heroic tradition of the word, test pilots, flag planters, representatives of human ambition. Think of them as what they actually are: operators of a closed-loop life support system on a planet where every second of survival depends on that system never, not once, failing. Every second alive on Mars is borrowed from engineering, and the loan has no forgiveness clause. There are 4 major categories of threat waiting for those operators, and we're going to go through every single one of them. Radiation that exceeds career limits before the mission ends. An atmosphere that kills in seconds and cannot be fixed with a better suit. Soil so saturated with a thyroid-destroying chemical that farming is essentially impossible. Dust storms that can swallow the entire planet and cut solar power to almost nothing for months. Any one of these would be a serious engineering challenge. Together, layered across 2.7 years of total isolation with no rescue available, they form something that has never been attempted in the history of human spaceflight. Something that the people planning it call a mission. Something that, if you look at it honestly, is closer to a prolonged survival experiment where the experiment ends if you fail. And we have not even talked yet about how you get there. Part 2. The timeline that doesn't add up. The Moon is 1.3 light seconds away. That sounds like an abstract measurement, but think about what it means practically. When Apollo 11 was in lunar orbit and the crew needed to talk to Houston, the message took 1.3 seconds to arrive. A back-and-forth conversation had a delay you could almost miss if you were not paying attention. When something went wrong on Apollo 13, engineers on the ground could talk to the crew, hear their response, and iterate on a solution in something resembling real time. The distance was enormous by any human standard. It was also, compared to what comes next, basically nothing. Mars, depending on where both planets are in their orbits, sits between about 3 minutes and 24 minutes away at the speed of light. At its farthest point, a signal from a crew on Mars takes 24 minutes to reach Earth. A response takes another 24 minutes to get back. You ask a question, and you wait 48 minutes for the answer. Now imagine that question is not about mission parameters or geological samples. Imagine the question is, we think there is a problem with the life support system. What do we do? You send the message. You wait 48 minutes. Whatever is happening to your life support system keeps happening for those 48 minutes, while the people who built it and know it best are physically incapable of responding faster. That is not a communication inconvenience. That is a fundamental restructuring of what a crewed mission even means. This communication gap is one of the reasons the timeline for actually getting humans to Mars does not add up the way the headlines suggest. NASA's Artemis program, which is intended to return humans to the Moon and establish the kind of deep space operational experience that a Mars mission would require, has seen its own schedule slip repeatedly. The first crewed lunar landing under Artemis, initially planned for 2024, has been pushed to Artemis 4, currently targeting around 2028, and the Moon is 1.3 light seconds away. If establishing a sustained human presence on the Moon, a body we have visited before, a body with no atmosphere to worry about, a body 2 or 3 days from Earth, is taking this long and this many iterations to get right, the jump to Mars is not a linear extension of that effort, it is an exponential one. SpaceX's Starship program, which would be the most plausible near-term vehicle for a crewed Mars mission, has made genuinely impressive progress. But the architecture for a Mars mission depends on orbital refueling, the ability to launch a ship into Earth orbit, refuel it from a separately launched tanker, and then send it onward to Mars with a full propellant load. That process has not yet been demonstrated at the scale a Mars mission would require. The technical challenge is real, and the timeline estimates from SpaceX itself have consistently shifted by 5 to 7 years from initial projections. This is not a criticism. It is simply the pattern that complex aerospace programs follow, and recognizing that pattern matters when someone tells you that boots are hitting Martian soil by 2029. There is also the sobering record of robotic Mars missions to consider. About half of all missions sent to Mars, robotic, uncrewed, carrying nothing but instruments, have failed. The planet has claimed orbiters, landers, rovers. It has claimed them through software errors, through atmospheric miscalculations, through hardware failures, through the 7 minutes of autonomous terror that every Mars entry, descent, and landing represents. And those missions had no crew to keep alive, no life support to maintain, no psychological endurance requirement. They were machines, and Mars still destroyed roughly half of them. Every robotic failure is a data point about the complexity of operating on Mars. And every data point, when you hold it against the central reality of this mission, 2.7 years, no rescue, no abort, crew fully dependent on technology for every breath, reminds you that the timeline humanity is working toward is not a calendar schedule, it is a capability schedule. We will go to Mars when we can actually survive going to Mars. The question worth asking, the question that shapes everything that follows in this video, is whether we are as close to that threshold as the press releases suggest. Part 3. The unspoken rule. Every human spaceflight mission in history has had an abort option. Not always a good one, not always one that guaranteed survival, but there has always been a path back to Earth that physics permitted, even if engineering or circumstance made it difficult. On Apollo 13, the service module exploded 200,000 miles from Earth, and the crew made it home using the lunar module as a lifeboat, because the geometry of the Moon's gravity allowed a free return trajectory, a path that swings around the Moon and uses its gravity to slingshot the spacecraft back toward Earth without requiring a major engine burn. The mission was a near catastrophe. It was also, crucially, recoverable. The laws of orbital mechanics permitted rescue. That permission is something so fundamental to how we think about space missions that most people have never even noticed it was always there. On a Mars mission, it is not. The moment a Mars-bound spacecraft fires its trans-Mars injection burn, the engine burn that commits the vehicle to the trajectory toward Mars, the crew is no longer in a position where Earth can reach them in any meaningful time frame. Mars launch windows open every 26 months. That is how long it takes for Earth and Mars to realign in their orbits, to a geometry where the journey between them is energetically feasible. Miss that window, and you wait another 26 months. There is no shortcut. There is no emergency window that opens if someone gets sick at month 4. The orbital mechanics that make Mars reachable also make it a trap once you commit. The mission structure is roughly this: 9 months of transit from Earth to Mars, approximately 15 months on the surface waiting for the orbital geometry to realign, then 9 months of transit back to Earth. 2 years and 7 months, give or take, depending on the specific launch window. The surface stay is not optional. It is not there because scientists want to maximize science return, though they do. It is there because the physics of the solar system require it. You cannot leave Mars whenever you want. You can leave Mars when the window opens, and not before. An early return is not dramatically difficult. It is, for most of the surface stay, physically impossible with any propulsion system we can realistically launch. This is the unspoken rule of Mars. Every previous human mission existed within a framework where, even in the worst case, return was a physics-permitted option that engineering could potentially pursue. Apollo, Space Shuttle, ISS crew rotations, all of them operated inside a gravitational and orbital environment where rescue was conceivable. Mars removes that framework entirely. The crew, once committed, is committed. Whatever happens on the surface happens to people who cannot be reached, cannot be rescued, and cannot come home until the window opens. Think about what that does to the psychology of a mission. We have some analogues. Antarctic winter overcrews spend months at stations where extraction is impossible due to weather. Submarine crews operate in total isolation for extended periods. These are demanding, psychologically rigorous experiences that give researchers insight into how humans endure isolation and confinement. But the Antarctic researcher knows that in a genuine emergency, a rescue attempt is at least theoretically possible if conditions change. The submariner knows the ocean they are in is the same ocean their home port sits on. The Mars crew knows something different. They know that the distance between them and every other human being who has ever lived is measured in light minutes, that no vehicle capable of reaching them will be launched in time to matter, and that whatever challenge they face it alone, with only each other and the equipment they brought. The psychological researchers call this autonomous operations under irreversible commitment. The translation is simpler than the terminology suggests. It means that knowing you cannot leave changes the way you think. It changes the decisions you make. It changes how you respond to setbacks, how you process fear, how you manage conflict with crewmates, how you handle the news from home that you receive with a 48-minute delay. It changes everything. And the problem is that we do not have good data on how humans perform under truly irreversible commitment, because no human has ever been in that situation before. Mars 500. The Russian experiment that confined 6 volunteers in a simulated Mars habitat for 500 days gave us partial data. But the participants knew they could walk out. That knowledge, even if they never used it, fundamentally changes the psychological dynamic. Remove it, and you are in territory that has no precedent. So the first Mars crew will not just be managing the physical hazards of a lethal planet. They will be doing it while carrying the full psychological weight of knowing that there is no abort, no escape, no recovery path that physics permits. What happens at month 4 when something breaks? We will get to that. First, we need to understand what kind of planet they're standing on and how it became this way. Part 4. Mars wasn't always dead. 4 billion years ago, if you could stand where the Curiosity rover now crawls across cracked rust-coloured rock and look around, you would not recognise the place. The sky above you would not be the thin butterscotch haze that modern Mars missions photograph. It would be thicker, heavier, the kind of sky that holds weather. You might see clouds. You might, depending on when in Mars's early history you arrived, feel something on your skin. Not warmth exactly. Not like a tropical afternoon on Earth, but something. The electromagnetic signature of a planet that had not yet lost the thing that made it capable of sheltering life. Mars had a magnetic field. Not a weak one. Measurements and models suggest it was comparable to Earth's, perhaps around 50 microtesla, strong enough to create a magnetosphere that deflected the solar wind and shielded the atmosphere from being stripped away particle by particle. Beneath that shield, Mars had air. Real air, by planetary standards, a carbon dioxide atmosphere thick enough to maintain surface pressure that liquid water could exist on the surface without immediately evaporating or freezing, and the evidence for what that water did is written everywhere you look on Mars, in every image the orbiters send back, in every sediment layer the rovers drill into. NASA's MAVEN spacecraft, which has been studying Martian atmospheric loss since 2014, has given us extraordinarily precise data on what Mars lost and how it lost it. The Perseverance rover's sediment analysis has confirmed what orbital imagery has long suggested, that ancient Mars had river systems, lake beds, possibly coastlines. The Noachian period, which ended roughly 3.7 billion years ago, shows evidence of widespread liquid water. Scientists debate the scale. Was it a few isolated lakes and rivers, or was there a genuine northern ocean? The debate continues. What does not continue is the water itself. It is gone, or frozen in the subsurface and at the poles. The rivers that carved those channels have been dry for billions of years. Here is why this matters for our crew, and why it is not just interesting geological backstory. Mars had everything. 4 billion years ago, Mars had the magnetic field, the atmosphere, the liquid water, the three things that together make a planet survivable for something like a human being. It had them, and it lost them. What the first Mars crew will be surviving is not some alien environment that was always this extreme. It is the end state of a process of planetary death. Every hazard they face, the radiation, the pressure, the toxic soil, the dust storms, every single one of those hazards exists because Mars used to be something it no longer is. That is the context. And what comes next is the story of how the most important planetary disaster in this solar system's history unfolded. Part 5. The moment it lost everything. Inside the Earth, right now, there is a churning mass of molten iron and nickel in the outer core that is in constant motion. That motion, driven by the rotation of the planet and the temperature difference between the inner and outer core, generates electric currents. Those electric currents generate a magnetic field. The field extends tens of thousands of kilometers into space, creating an invisible bubble, the magnetosphere, that deflects most of the charged particles streaming outward from the sun. You're alive in part because of that field. Strip it away, and the solar wind begins systematically dismantling the atmosphere. Strip the atmosphere, and the water evaporates or freezes. Strip the water, and you have Mars. The question of exactly why Mars lost its magnetic field is one of the most actively studied problems in planetary science, and the answer is almost certainly related to its core cooling faster than Earth's. Mars is smaller, about half Earth's diameter, roughly 10% of Earth's mass. Smaller planets lose internal heat faster, and there are competing hypotheses about exactly how the Martian dynamo shut down. Some researchers point to core cooling as the primary driver. Others suggest that major asteroid impacts during the late heavy bombardment could have disrupted the magnetic field directly, either by altering core convection or by depositing enough energy to temporarily interfere with the dynamo. There may also have been changes in mantle heat flow, the way heat moves from the interior toward the surface, that shut down the convective engine driving the field. The exact mechanism is still debated, the consequences not. Once the magnetic field weakened and eventually collapsed, the solar wind had direct access to the Martian atmosphere. And the solar wind is not a gentle thing. It is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the sun at 400 to 800 kilometers per second. When those particles hit an unshielded atmosphere, they interact with the upper atmospheric gases and gradually transfer enough energy to eject them into space. The process is called atmospheric sputtering, and it is slow by human timescales and catastrophic by geological ones. MAVEN's data put specific numbers on this. The spacecraft measured that Mars is currently losing roughly 100 grams of atmosphere per second to solar wind stripping. 100 grams per second sounds small. Integrated over the 4 billion years since the magnetic field collapsed, it represents an atmospheric loss equivalent to approximately 0.8 bars of carbon dioxide pressure. To put that in human terms, Earth's entire atmosphere is about 1 bar of pressure. Mars lost nearly an entire Earth-equivalent atmosphere. Slowly, inexorably, particle by particle, the solar wind took it. As the atmosphere thinned, the greenhouse effect that had kept Mars warm enough for liquid water diminished. Surface temperatures dropped. Liquid water could no longer persist on the surface. It froze or sublimated directly into the thin air. The rivers ran dry. The lakes evaporated. The process took hundreds of millions of years, not overnight, and that gradual timescale is part of what makes it so difficult to fully visualize. Mars did not die in a cataclysm. It died slowly, in a kind of planetary exsanguination, losing its protective field, then its air, then its water, over timescales so enormous they make all of human history look like a rounding error. What remains is the environment our crew will have to survive. Every radiation reading the Curiosity rover has taken on the Martian surface, and we will get into exactly what those readings mean for a human body shortly, as a direct consequence of that magnetic field loss. Every atmospheric pressure reading that tells us the surface pressure is about 610 pascals is a record of the billions of years of atmospheric stripping that followed. The toxic chemistry of the soil, the behavior of the dust, even the nature of the dust storms, all of it traces back to the moment Mars lost the thing that made it habitable. The crew will be operating in the aftermath of one of the most complete planetary transformations in solar system history. And there is no engineering solution that fixes that. There is only engineering that compensates for it, imperfectly, for as long as the systems hold. Part 6. Why this should make you uncomfortable. There is an uncomfortable footnote to the story of Mars's magnetic field collapse, and it deserves a few paragraphs even though it is not the main story we're telling today. Earth's magnetic field is weakening. Not dramatically, not on any human-relevant timescale in any catastrophic sense, but the measurements are unambiguous. The field has weakened by roughly 5% over the last century, and satellite data shows the South Atlantic anomaly, a region where the field is unusually weak, is expanding. The planet experiences geomagnetic reversals, events where the north and south magnetic poles swap positions, on average every several 100,000 years. The last one was about 780,000 years ago. We are statistically overdue. No serious planetary scientist argues that Earth is becoming Mars. The situations are not comparable. Earth's core is far more energetically active. Our planet is larger. Our dynamo is far more robust. A geomagnetic reversal would be disruptive in ways that would affect satellites and navigation, but it would not lead to atmospheric stripping on any relevant timescale. Earth is not dying the way Mars died. That is important to say clearly. But Mars is still worth holding up as a reference point. Not as a prophecy, but as a reminder that planetary habitability is not a permanent condition. It is a balance. Mars had the balance, and it lost it. The crew heading to Mars will be standing on proof of what happens when a planet cannot maintain the conditions that shelter life, and that proof will be in every reading their instruments take, every breath their suits manufacture, every radiation alarm their dosimeters record. Mars is not just a destination, it is a data point about the fragility of the conditions that allow something like us to exist at all. And now, let us talk about what those conditions, in their absence, actually do to a human body. Part 7. Radiation. The Invisible Countdown. The Curiosity rover has been quietly rewriting the risk profile of Mars for over a decade, not through dramatic discoveries or visual spectacle, but through something far more clinically important: numbers. Since its landing in August 2012, it has carried an instrument called the Radiation Assessment Detector, or RAD, which has been measuring the radiation environment on and above the Martian surface continuously. What makes RAD especially valuable is that it did not start its job on Mars. It began recording during the 7-month journey through deep space, meaning we now have a continuous radiation profile from Earth orbit, through interplanetary space, down to the Martian surface itself. That continuity is what allows scientists to build a realistic model of what a human body would actually experience on the journey. The surface numbers it returned were both expected and unsettling. On average, the Martian surface delivers about 0.64 millisieverts of radiation per day. That figure sounds abstract until it is placed next to Earth's background radiation levels. A typical person on Earth receives roughly 3 millisieverts per year from all natural and medical sources combined. That includes cosmic rays filtered through the atmosphere, trace radioactive materials in the soil, and even small doses from medical imaging. When you convert Curiosity's Martian reading into yearly exposure, it comes out to roughly 230 millisieverts per year. That is about 75 to 80 times higher than what a person experiences at sea level on Earth, and importantly, that is only the surface environment. It does not include the journey there or back. The transit phase is where the numbers become even more significant. A full round-trip Mars mission, depending on trajectory and solar conditions, is estimated to expose astronauts to somewhere between 625 and 1,650 millisieverts of radiation in total. That range is wide because space is not a stable radiation environment. It changes with the sun's activity cycle. During solar minimum, when the sun is relatively quiet, the shielding effect of the heliosphere weakens, allowing more galactic cosmic rays to penetrate the inner solar system. During solar maximum, the increased solar activity partially deflects those galactic rays, but introduces a different hazard in the form of solar particle events, which are sudden bursts of high-energy radiation that can spike exposure dramatically in short periods of time. To understand why this is such a difficult engineering problem, it helps to separate the two main radiation sources. Galactic cosmic rays, or GCRs, are constant. They are not tied to solar weather or predictable cycles in any useful short-term sense. They originate from outside the solar system, often from supernova remnants or other high-energy astrophysical processes, and they consist of extremely energetic particles, including what physicists call high-Z'd, high-energy particles. These are heavy atomic nuclei such as iron ions travelling at relativistic speeds. When these particles strike human tissue, they do not behave like ordinary radiation. They create dense tracks of ionization, essentially microscopic trails of damage through cells and DNA structures. The intuitive solution would be shielding, build thicker walls, add more material between the crew and space. But in deep space radiation physics, that intuition breaks down in an important way. When high-energy particles strike shielding materials like aluminum, they can produce secondary radiation. Instead of stopping the threat cleanly, the shielding can fragment the incoming particle into a shower of lower-energy particles. Some of those secondary particles can actually deposit more biological damage in tissue than the original particle would have caused alone. This is not a trivial engineering flaw. It is a fundamental interaction between high-energy physics and matter. It means that simply adding more mass is not a guaranteed solution. It becomes a trade-off problem involving material composition, thickness, spacecraft mass limits, and biological effectiveness of different radiation types. There are alternative shielding ideas, such as using hydrogen-rich materials like polyethylene, or even water walls, which are more effective at slowing and absorbing certain types of particles. There are also more speculative concepts involving electromagnetic shielding, where magnetic fields would deflect charged particles away from the spacecraft. But all of these solutions come with trade-offs in weight, energy consumption, or engineering complexity. And every kilogram launched to Mars has an enormous cost in propulsion, fuel, and mission design constraints. This is why, despite decades of research, there is still no perfect radiation shield for interplanetary travel. There are only partial mitigations. The second major radiation threat is solar particle events, or SPEs. Unlike galactic cosmic rays, these are intermittent and tied to solar activity. They occur when the sun releases bursts of energetic particles during flares or coronal mass ejections. These events can vary dramatically in intensity, Many are harmless or minor. Some, however, are powerful enough to deliver a significant radiation dose in a matter of hours. On Earth, we are largely protected by our magnetic field and atmosphere. In interplanetary space or on the surface of Mars, that protection is absent or severely reduced. The operational response to a solar particle event is conceptually simple, but physically constrained. The crew must move into a heavily shielded section of the spacecraft or habitat, often referred to as a storm shelter. These are areas designed with extra material density, sometimes surrounded by water tanks or supplies, to provide temporary protection. This strategy works for moderate events and provides critical survival margin during warning periods. The challenge is that prediction is imperfect. Some solar events provide hours of warning, others provide only minutes, and in extreme cases a fast-developing event could begin delivering dangerous radiation doses before full sheltering is achieved. There is historical evidence that extreme solar particle events have occurred in the past, far stronger than anything observed in the modern space age. If an astronaut had been unprotected in deep space during one of those events, the radiation dose could have exceeded acute safety thresholds in a very short time. This is not theoretical risk in the abstract sense. It is a known class of events that has simply not yet intersected with human presence outside Earth's protective environment. While solar events create acute risk, galactic cosmic rays create chronic risk. This is where the long-term concern becomes more subtle and, in some ways, more troubling. Chronic exposure does not cause immediate illness. Instead, it accumulates damage over time. DNA repair systems in the body can correct many radiation-induced breaks, but not all of them. Over long durations, the probability of replication errors increases, which is why cancer risk is a central concern in Mars mission planning. However, cancer is not the only issue. Research conducted at facilities like NASA's Space Radiation Laboratory at Brookhaven National Laboratory has shown that simulated deep space radiation environments can produce measurable effects on the central nervous system in animal models. These experiments use particle accelerators to replicate high-energy heavy ions, similar to those found in cosmic rays. In rodent studies, exposure to these particles has been linked to changes in brain inflammation patterns, synaptic density, and neural connectivity. The behavioral outcomes are equally important. Animals exposed to these conditions show differences in memory tasks, increased anxiety-like behavior, and changes in decision-making performance. The critical concern for human missions is not just that these effects exist, but that they accumulate in a way that may not produce obvious early warning signs. The brain does not have a pain receptor for cognitive degradation. A crew member does not feel synaptic density slowly changing over months. If similar effects occur in humans, they may manifest as subtle shifts in reaction time, emotional regulation, or complex decision-making under stress. In a mission environment where decisions are already high stakes, and where communication delays prevent immediate consultation with Earth, even small cognitive changes could have operational consequences. The most difficult aspect of this is timing. A Mars mission is long enough that crew members are exposed to significant radiation before they reach the surface, then continue to be exposed during surface operations, and finally again during return transit. That means any cumulative neurological or physiological effects are not isolated to a single phase of the mission. They occur while the crew is still responsible for running life support systems, conducting surface operations, responding to emergencies, and maintaining group stability in an isolated environment. In other words, the radiation does not just accumulate in the background. It accumulates while the mission is still actively relying on peak human performance. There is also a more unsettling possibility that researchers are only beginning to explore, that the effects of long-duration exposure might not be linear or easily predictable. Cognitive performance could degrade in ways that are context-dependent, showing up only under stress or in complex decision environments. That would make detection extremely difficult until a critical moment forces the issue. All of this creates a layered picture of risk that is not dramatic in the cinematic sense, but deeply structural. Radiation is not a single hazard to be solved. It is a constant background condition of deep space travel, one that interacts with every other part of the mission. It affects vehicle design, mission timing, crew selection, operational procedures, and even psychological resilience. And unlike many engineering problems, it does not go away with better training or improved protocols. It is built into the environment itself. Which brings us back to the larger question that underlies all of this. If a crew is exposed to this level of continuous radiation, while simultaneously living in isolation, managing life support systems, and operating on a planet that is itself hostile to human biology, what does that do not just to the body, but to the quality of human decision-making over time? Because radiation does not act alone. It is one variable in a system where every variable is already under extreme stress, and that is where the real complexity begins. Part 8. The Atmosphere Problem. Nobody explains properly. Standing on Mars without a suit is one of those thought experiments that sounds like it belongs in science fiction until you start running the numbers. At first, people tend to imagine the obvious dangers: freezing temperatures, lack of oxygen, maybe a slow suffocation as the air becomes unbreathable. But none of those are actually the limiting factor. The real answer is far more abrupt, far less forgiving, and surprisingly short. You do not have minutes. You do not even have enough time to react in any meaningful way. You have roughly 10 to 15 seconds of usable consciousness before the body begins to fail in ways that are rapid, systemic, and irreversible. To understand why, you have to start with pressure, because pressure is the invisible condition that allows human biology to function at all. On Earth at sea level, the atmospheric pressure is about 101,300 pascals. That constant push of air against the body is what keeps fluids stable at normal temperatures. On Mars, the surface pressure averages around 610 pascals. That is less than 1% of Earth's atmosphere. It is not just thin air in the poetic sense. It is a near vacuum by Earth standards, an environment where the rules that keep liquid stable begin to fall apart in very literal ways. The key concept here is something called the Armstrong limit, which sits at about 6,300 pascals. Below that threshold, water can boil at roughly human body temperature. Mars is well below that limit. That means that any exposed moisture on your body is no longer in a stable liquid state. It does not explode in a cinematic burst, but it does begin to transition into vapor in a way that is deeply disruptive to living tissue. The surface of the eyes, the lining of the mouth, the moisture in the lungs, all begin to behave as if they are no longer properly contained. Fluids expand into gas pockets, tissues swell, and the body starts to experience a form of internal disruption known as ebulism. Ebulism is not a dramatic boiling over of blood as often depicted in movies. That image is misleading, but the truth is in some ways more disturbing. The circulatory system is protected because it is pressurized, so blood does not immediately vaporize. Instead, the most vulnerable areas are those not protected by internal pressure: the lungs, the eyes, the mucous membranes. In those regions, gases form where they should not exist. Cells begin to rupture under pressure differentials. Oxygen exchange collapses almost immediately because there is no breathable oxygen in the Martian atmosphere, which is itself about 95% carbon dioxide at a density far too low to sustain respiration even if it were chemically suitable. Carbon dioxide toxicity becomes irrelevant in a strange way because you do not survive long enough for it to matter. On Earth, elevated CO2 levels cause hypercapnia, a condition where the blood becomes acidic and the nervous system begins to fail. On Mars, the limiting factor is not chemical poisoning but the inability to maintain pressure and oxygenation at the same time. The first breath would not help. It would only accelerate the collapse of oxygen exchange in the bloodstream. Even the act of trying to breathe becomes physiologically meaningless almost instantly. The result is a very narrow window of awareness. 10 to 15 seconds is the commonly estimated range for useful consciousness in such conditions, though even that depends on individual variation and exact exposure conditions. During those seconds, cognitive function remains intact just long enough for the brain to register that something is catastrophically wrong. After that, oxygen deprivation accelerates, neural activity drops, and consciousness fades. Importantly, this is not a gradual fading like sleep. It is a sharp descent into unconsciousness, driven by the failure of the brain's oxygen supply system, under conditions it was never evolved to tolerate. What happens next is purely biological and no longer experiential. The body continues to respond to the environment, but the person is no longer present in any meaningful sense. The damage proceeds through tissue expansion, gas formation in fluid spaces, and rapid systemic failure at the cellular level. Even though the term explosive decompression is often used in popular media, the reality is more restrained but still fatal. The body does not burst outward, but it does begin to lose structural integrity in a way that cannot be reversed without immediate recompression, which is impossible in this scenario. This is why the engineering challenge of Mars is not simply about keeping astronauts comfortable or warm or supplied with oxygen. It is about maintaining a continuous artificial environment that prevents a transition into this regime entirely. A spacesuit on Mars is not clothing. It is not insulation. It is not even primarily protection from temperature. It is a portable pressure vessel, essentially a miniature spacecraft that happens to be shaped like a human body. Every seam, every joint, every glove interface is a potential failure point that must be designed to near-perfect reliability because there is no margin for gradual degradation. A tiny puncture that would be a maintenance issue on Earth becomes a life-ending event on Mars within seconds. A microscopic fracture in a visor, invisible under normal inspection conditions, could propagate under thermal cycling and radiation exposure until it compromises the pressure boundary. A degraded seal in a glove joint could leak slowly enough to go unnoticed until the internal pressure drops below survivable levels. In each case, the problem is not that failure is likely in a statistical sense on a single use, but that over hundreds of extravehicular hours across multiple crew members, the probability of something going wrong becomes non-negligible, and on Mars, non-negligible risk accumulates into real events with no rescue option. This is why redundancy is built into every layer of the system. Multiple seals, pressure sensors, automatic shutdown protocols, and rapid return procedures are not optional features but fundamental requirements of survival architecture. The suit constantly monitors its own integrity, looking for pressure drops or micro leaks before they become catastrophic. The habitat functions as a backup pressure system, and airlocks are designed as controlled transition zones that minimize contamination and exposure time. But even with all of this, the core reality remains unchanged. The environment outside is incompatible with human life in a way that allows no improvisation. What makes this more psychologically significant is that all of these systems operate continuously under stress. A Mars mission is not a sequence of safe moments punctuated by danger. It is a continuous state of managed vulnerability. Every EVA is a controlled exposure to a lethal environment. Every return to the habitat is a procedural race against contamination and system integrity. And all of this happens while the crew is also managing radiation exposure, dust infiltration, mechanical wear, communication delays, and the psychological weight of long-term isolation. The atmosphere itself becomes a kind of silent adversary. It does not need to act aggressively because it simply never allows relaxation of constraints. There is no moment on the surface where a human can exist without technological mediation. Even brief exposures outside a suit are not survivable interruptions but fatal errors. This creates a condition where safety is not a baseline but a constantly maintained achievement, and where the absence of failure is not normality but success under continuous pressure. In that sense, Mars is not dangerous in the way most environments are dangerous. It is not a place where you can recover from mistakes. It is a place where the concept of a small mistake does not exist in the same way. Every breakdown of the pressure boundary is absolute. Every exposure is total. Every second outside the suit is part of a tightly bounded window between survival and irreversible physiological collapse. And that is the underlying truth revealed by this thought experiment. The Martian surface does not negotiate with human biology. It does not gradually become dangerous. It simply is incompatible, and the only reason humans can interact with it at all is because we bring an entire self-contained environment with us, one that must function perfectly, continuously, and without interruption for as long as we remain there, streaming interrupted, waiting for the complete message. Part 9. The surface is toxic. Even if everything mechanical behaves exactly as designed, even if every seal holds and every system performs with intolerance, Mars still presents a kind of slow-burn threat that doesn't announce itself with alarms or catastrophic failure. It seeps in through chemistry, through dust, through the basic fact that the surface is not just barren but actively hostile at a molecular level. And unlike radiation or vacuum exposure, which are immediate and obvious, this one works quietly, accumulating in the background of daily life until it becomes part of the environment you stop noticing. The central issue is a class of compounds called perchlorates. These are salts built around highly oxygen-rich chlorine chemistry, and while they exist naturally in small amounts on Earth, they are tightly controlled because of their biological effects. In regulated water systems, the acceptable exposure threshold is measured in parts per billion, a scale so small it is easy to misinterpret. 2 parts per billion is considered safe in drinking water standards in the United States, meaning that anything above that level begins to trigger concern about long-term endocrine disruption, especially for sensitive populations. It is an extremely conservative limit, shaped by decades of toxicology studies that look at chronic exposure over time rather than acute poisoning events. Now place that number next to what we have actually measured on Mars. When NASA's Phoenix lander analysed Martian soil, it detected perchlorate concentrations in the range of roughly 0.5% to 1% by weight. That sounds abstract until it is translated into the same scale used in Earth safety regulations. It is not slightly elevated. It is not even in the same category of exposure. It is millions of parts per billion, spread throughout the very material that makes up the planet's surface layer. In other words, the Martian ground is chemically normal for Mars but fundamentally incompatible with Earth-based biological safety assumptions. The main biological concern with perchlorates centers on the thyroid gland. The thyroid is one of those quiet regulatory systems in the body that most people never think about until something goes wrong. It controls metabolic rate, energy balance, temperature regulation, and indirectly influences mood, cognition, and cardiovascular function through hormone production. It does this by absorbing iodine and converting it into hormones that circulate through the bloodstream. Perchlorates interfere with this process by competing with iodine uptake, effectively blocking the thyroid from doing its job. The result, if exposure is significant or prolonged, is hyperthyroidism, a condition where the body's metabolic systems slow down and begin to malfunction in subtle but widespread ways. This is not an immediate dramatic failure mode. It is not like decompression or radiation sickness. It is gradual. Fatigue increases, cognitive sharpness declines slightly, cold tolerance worsens, recovery from physical exertion becomes slower. On Earth, these symptoms are treatable and manageable, but they are also easy to overlook in early stages, especially in environments where fatigue and stress are already expected. That is what makes the Martian context particularly concerning. The environment itself already pushes human physiology towards strain, and perchlorate exposure adds another layer of pressure that is difficult to isolate or diagnose in real time. The reassuring part, and it is important not to dismiss it, is that astronauts will not be consuming Martian soil or water directly. Life support systems will be designed to be closed-loop, meaning food, water, and air are carefully controlled and continuously recycled. Direct ingestion of perchlorates at Martian surface levels is preventable with proper engineering. The more complicated issue is indirect exposure through dust, because dust is everywhere, unavoidable, and behaviourally difficult to contain over long durations. Martian dust is not like Earth dust. It is extremely fine, often in the range of 1 to 2 micrometers, small enough to remain suspended in the thin atmosphere for extended periods, and small enough to behave almost like a gas in some conditions. During global dust storms, which can envelop the entire planet for weeks or months, this material becomes a persistent airborne presence. It penetrates equipment seams, coats solar panels, adheres to suit fabric, and infiltrates mechanical systems with a persistence that engineers describe as almost invasive. The electrostatic properties of the dust, combined with the low humidity and weak atmospheric pressure, cause it to cling aggressively to surfaces rather than simply settling. Every extravehicular activity becomes a transfer event. A suit goes outside, collects dust, returns to the airlock, and even after cleaning protocols, microscopic particles remain embedded in folds, joints, and surface textures. Over time, small amounts of this material inevitably migrate into the habitat. Air filtration systems will remove the majority of particulates, but majority is not the same as all, especially over hundreds of days of repeated exposure. The concern is not a sudden spike in contamination, but a gradual background level of inhalation that never fully drops to zero. This is where perchlorates re-enter the picture in a more subtle way. The compound is not just sitting harmlessly in the soil, it is part of the dust matrix that gets redistributed into the environment. Even trace inhalation over long periods raises questions about cumulative endocrine effects, especially when combined with other stresses like radiation exposure and physiological deconditioning in low gravity. The problem is not a single dose, but the layering of multiple small exposures across time, each one individually manageable, but collectively difficult to model with precision. What makes this even more complex is that the same chemistry that creates the hazard also intersects with potential solutions. Perchlorates, for example, can be broken down thermally to release oxygen. This is not just a laboratory curiosity, it is directly relevant to Mars engineering concepts that aim to produce breathable air, or even rocket propellant from local materials. Systems like NASA's MOXIE experiment on the Perseverance rover already demonstrated oxygen extraction from carbon dioxide in the Martian atmosphere. But scaling life support and fuel production to human mission levels may involve processing large volumes of surface material where perchlorates are present. This creates an unusual paradox. The planet's toxic chemistry is also part of its resource potential. The same compounds that complicate human habitation might also become inputs for survival infrastructure. It is a kind of forced cohabitation with the environment at a chemical level. You do not get to separate the dangerous parts from the useful ones cleanly. They are embedded in the same system. When you step back, what emerges is not a single problem but an ecosystem of overlapping constraints. Radiation accumulates silently in the body over time. Dust infiltrates habitats despite engineering controls. Perchlorates interfere with endocrine function at trace levels. Each of these challenges is manageable in isolation within certain margins of error, but Mars does not present them in isolation. It presents them simultaneously, continuously, and without the possibility of external repair or evacuation in real time. This is the deeper reality of living on Mars. It is not a place where survival is threatened by one dramatic failure point. It is a place where survival depends on managing dozens of slow, interacting pressures that never fully go away. The suit might hold perfectly. The habitat might remain pressurized. The radiation shielding might perform as expected. And still, the environment outside and the residue of that environment inside will continue to shape the body and mind in ways that are gradual, cumulative, and difficult to fully predict. Mars does not need to break things suddenly to be dangerous. It only needs to keep existing exactly as it is. Part 10. Dust Storms That End Missions. In June of 2018, a dust storm began near the Perseverance Valley on Mars. It started small, a regional disturbance, the kind of thing Mars does regularly, the atmospheric equivalent of a bad weather week. Meteorologists tracking the Martian atmosphere from orbit noted it, logged it, and kept watching. By July, it had grown into something more serious. By midsummer, it had become a global event, an atmospheric phenomenon that covered virtually the entire planet in a blanket of suspended dust so thick and so pervasive that it reduced sunlight reaching the surface to a fraction of normal levels. Not a regional inconvenience, a planetary one. Mars had, in the span of a few weeks, wrapped itself in a shroud. The Opportunity rover was on the other side of the planet when it started. Opportunity had been exploring Mars since January of 2004, nearly 15 years of surface operations at that point, which is one of those facts that stops you mid-sentence when you really sit with it. It was designed as a 90-day mission. 90 days. Scientists and engineers had hoped, if things went well, that it might last a year. It lasted 15 years, crawling across the Martian surface, sending back data, surviving dust devils and cold nights, and every challenge the planet had thrown at it across more than 5,000 Martian days. It was, by any honest measure, one of the most successful robotic missions in human history. And then the storm arrived. Opportunity relied on solar panels to generate electricity for everything it needed: movement, communication, heating, instrument operation. Every system on that rover, every function it performed, drew from the power those panels produced. As the storm's optical depth increased, meaning the atmosphere became increasingly opaque to sunlight, loaded with more and more suspended particles that scattered and absorbed the incoming radiation before it could reach the surface, Opportunity's power generation began to crash. Not slowly, not in a way that gave engineers time to plan elegantly around it. Fast. Within 3 days of the storm reaching its full intensity, Opportunity's solar panels were producing almost nothing. The rover went into a low-power hibernation mode, conserving what little energy remained in its batteries. It sent one final communication to Earth. Then it went silent. The optical depth during the 2018 global storm reached levels where only about 1% of normal sunlight was reaching the surface at Opportunity's location. Let that number sit for a moment. 1%. The Sun, which on a clear Martian day already appears roughly 2/3 the size it does from Earth, because of the greater distance, was functionally invisible. An atmosphere so loaded with suspended particulate matter that the star at the centre of our solar system, the thing that makes every form of energy on that planet ultimately possible, had been effectively erased from the sky. The rover could not charge its batteries. The batteries drained. The heaters that kept the electronics from freezing in the -60 or 70 degrees Celsius Martian nights went offline. The equipment froze, and the mission ended. 15 years ended in days. I want you to hold that image for a second before we move on, because it is doing a lot of work in this story. A machine that had survived 15 Martian years, 5,000 Martian days of cold and dust and mechanical stress, and the general hostility of an alien environment, was undone not by a catastrophic failure, not by a software error, not by a design flaw. It was undone by the sky going dark, by the sun disappearing behind a curtain of suspended dust that the planet itself generated, spread and sustained for months. No engineering failure, no human error, just Mars being Mars, doing what Mars does, on a time scale that overwhelmed the system designed to survive there. Now I want you to do something uncomfortable. Replace Opportunity with a human crew. Replace the solar panels with the habitat's power generation system, the system responsible for maintaining atmospheric pressure inside the habitat, regulating temperature, running the water recycling unit, producing oxygen, keeping the communication array functional, and powering the medical equipment. Replace the hibernation mode with a crew of 4 or 5 people, watching their power reserves decline in real time, knowing that the systems keeping them alive are drawing from a battery bank that is not being replenished, because the sky outside is the colour of rust, and the solar panels are generating almost nothing. And replace the mission ended with something the mission report will never use that phrase to describe: a scenario where the crew is managing a life support crisis on a planet they cannot leave, in a storm that may last weeks or months, with no rescue possible and a communication delay to Earth that means every question they ask takes nearly an hour to get an answer. The storm does not kill the crew directly, the way that radiation or atmospheric exposure would. It does not reach through the habitat walls and harm them. What it does is slower and in some ways more insidious. It starves the systems the crew depends on to stay alive, and it does so at a rate and over a duration that can exceed any reasonable battery backup capacity. You cannot bring enough batteries to Mars to outlast a global storm that lasted months. The mass alone would make the mission architecture impossible, so the crew manages. They reduce power consumption, they shut down non-essential systems, they prioritize, they make decisions about what they can live without and what they absolutely cannot, and they make those decisions in real time, under stress, with a 48-minute round-trip communication delay to the people on Earth who know the systems best. This is where it is worth understanding how Mars storms actually work, because the 2018 event was not a freak occurrence. It was a category of thing that Mars does, on a schedule, with a predictability that makes it not a question of if, but of when. Dust storms on Mars are categorized by scale. Local storms are relatively common, confined to a region, lasting days to weeks, causing temporary solar power disruptions, but not necessarily creating an existential power crisis for a crew with reasonable battery reserves. They are manageable, annoying, operationally disruptive, but manageable. Regional storms are more serious, larger in area, longer in duration, capable of persisting for weeks or months, capable of reducing solar power output significantly across a wide area. A regional storm during a critical mission phase, a planned EVA, a system repair, a resource production cycle, introduces real risk. And global storms like the 2018 event are the most extreme category. They are the ones that turn the sky opaque. They are the ones that end rovers. Global storms are relatively rare in any given Martian year. That sentence sounds reassuring until you do the arithmetic. The crew's surface stay is 15 months, roughly 7.5 Martian years, because a Martian year is about 687 Earth days. Over 7.5 Martian years, the probability of encountering at least one significant regional storm approaches certainty. The probability of a global event is non-trivial, and there is a further complication that makes the timing worse. The Martian storm season, the period when dust lifting is most vigorous due to increased atmospheric circulation and temperature gradients, coincides with the southern hemisphere summer, which is also when Mars is closest to the Sun in its slightly elliptical orbit. The crew's 15-month surface window, depending on the specific launch opportunity, will almost certainly overlap with at least part of that storm season. The planet's most dangerous atmospheric period and the crew's surface stay are not on different schedules, they are on the same one. Now here is where it gets elegant in the worst possible way. The storm does not just block sunlight, it also deposits dust. Martian dust carries an electrostatic charge. This is a property of the dust particles themselves. In the very low humidity, low pressure environment of the Martian surface, particles develop static charges that make them adhesive in a way that is extremely difficult to counteract passively. This is why the Opportunity rover's panels, even in the years before the final storm, accumulated dust coatings that slowly degraded their efficiency. It is also why the proposed solutions, using vibration systems to shake dust off panels, designing panel surfaces with reduced adhesion properties, remain engineering challenges rather than solved problems. The dust does not just settle, it clings, and it clings to everything, including the solar panels that the crew depends on for power. So during and after a storm event, the crew faces a layered problem. The atmosphere is opaque, which reduces solar power generation. The panels are accumulating a dust coating that further reduces efficiency even when the sky clears. And the solution to the second problem, physically cleaning the panels, requires EVAs, going outside, suiting up, cycling through the airlock, walking to the solar arrays with cleaning equipment, and manually removing the dust coating from panels that may be dozens of meters from the habitat. In deteriorating visibility, in a dust environment that is actively loading the suit's exterior with additional perchlorate-laden particles with every minute spent outside. While the power situation they went outside to fix is simultaneously limiting the power available for the suit systems they need to safely go outside in the first place. The suit life support runs on power. The power comes from the panels. The panels need cleaning. Cleaning requires suits. The suits need power. Mars does not offer a way out of that circle. It just tightens it. This is what engineers and mission planners sometimes call a coupled failure mode, a scenario where the response to a problem requires resources that the problem itself is depleting. It is not unique to Mars. Aviation has coupled failure modes. Submarine operations have them. But on Mars, the consequence of not breaking the loop is not a mission setback. It is a dead crew on a planet that cannot help them, and a planet that is 48 communication minutes from anyone who might try. The engineering community has not ignored this problem. Nuclear power, specifically small fission reactors, is the most discussed answer to the solar dependency issue. NASA's Kilopower project has made genuinely meaningful progress toward a compact fission reactor, roughly the size of a kitchen trash can, capable of producing around 10 kilowatts of continuous electrical power independent of sunlight. 10 kilowatts is not enormous. A modern American home uses roughly that much on average. But for a Mars habitat designed for extreme power efficiency, it could be enough to maintain the critical life support functions through even a months-long global storm. The kilopower technology is real. The progress is real. This is not vaporware. But it adds mass to the mission, and mass is the currency that every Mars mission architecture is perpetually short of. Every kilogram of reactor system launched to Mars is a kilogram that cannot be food, water, medical supplies, or redundant life support components. The reactor also requires its own engineering infrastructure, shielding to protect the crew from its radiation output, thermal management systems to handle the heat it generates, safety systems to manage it in the event of a habitat emergency. And it represents one more system that has never been operated in the actual Mars environment before. One more system that will encounter conditions, the dust, the temperature extremes, the radiation environment, the perchlorate chemistry, that no ground-based test can fully replicate. One more system that, if it fails on a planet with no replacement parts, no repair crew flying in from Earth, and no margin. There is a phrase that comes up in discussions of Mars mission engineering with a frequency that starts to feel like a warning. Every solution to a Mars problem introduces at least one new Mars problem. The nuclear power answer to the solar vulnerability problem is a genuinely good answer. It is probably the right answer, and it brings with it a new mass problem, a new radiation management problem, a new system complexity problem, and a new untested environment problem. Mars does not let you solve things cleanly. It just moves the difficulty around, redistributes it, and waits to see where it surfaces next. The storm that ended opportunity lasted long enough to drain a rover that had survived 15 years. The first crew on the Martian surface will watch the same skies that Rover watched, from inside a habitat that needs electricity to keep them breathing, and they will do the math in real time. And somewhere in that math, in the gap between the power reserves and the storm duration, and the suit life support requirements, and the cleaning schedule and the nuclear backup systems, and the 48-minute delay to Earth, is the actual texture of what it means to live on Mars, not the concept art, the math. Part 11. The engineering problem that doesn't have a solution. The single most dangerous moment of any Mars mission is not on the surface. It is not the radiation that slowly accumulates over months, or the toxic soil, or the dust storms that can swallow the planet for weeks at a time. It is 7 minutes long, 7 minutes between the top of the Martian atmosphere and the ground. This is the entry, descent, and landing sequence, EDL, and it is the most unforgiving, least understood, and least solved phase of the entire mission. Everything else in a Mars mission can fail slowly. EDL fails instantly. Here is the constraint stripped down to its most brutal form. Mars has an atmosphere, but it is the worst possible kind of atmosphere for landing anything heavy. It is thick enough to matter, but too thin to save you. When a spacecraft approaches Mars, it is not drifting in gently. It is moving at interplanetary speed, around 20,000 kilometers per hour. At that velocity, the moment it touches the upper atmosphere, it begins to slam into gas molecules with enormous energy. Friction builds immediately. Temperatures rise to thousands of degrees. Plasma forms around the vehicle, cutting off communication, so you need a heat shield. That part, at least, we understand. Missions like the Perseverance rover have demonstrated that we can survive this initial phase. But heat shielding only solves the first part of the problem. It slows you down just enough to reach the next impossible step. On Earth, that next step is where parachutes take over. The atmosphere is dense enough for a parachute to bite into the air, converting speed into drag and bleeding off velocity until the spacecraft reaches a manageable descent rate. Mars does not give you that luxury. Its atmosphere is only about 1% as dense as Earth's. That means a parachute behaves very differently. To compensate, you would need a parachute of enormous size, far larger than anything ever deployed at supersonic speeds. But that introduces a second problem. Parachutes do not just need to be large, they need to survive deployment. Imagine opening a parachute while travelling faster than the speed of sound. Now imagine that parachute being the size of a football field. The forces involved are extreme, too large, and the parachute tears itself apart the moment it inflates. Too small, and it does not slow you down enough. Mars sits exactly in the middle of that problem. The atmosphere is dense enough to destroy a large parachute during deployment, but too thin for a smaller parachute to be effective. It is the worst possible balance, so engineers have had to get creative. The landing of the Perseverance rover is often described as a triumph of engineering, and it is, but it is also a demonstration of just how complex and fragile this process really is. Perseverance did not rely on a single system. It relied on a chain of systems, each one dependent on the last. First, the aeroshell absorbed the initial energy of entry. Then, once the vehicle slowed enough, a supersonic parachute deployed, not at a safe speed, but at a survivable one. After that, the heat shield was jettisoned, exposing the rover and allowing onboard systems to begin actively navigating. At this point, the spacecraft was no longer just falling, it was thinking. Using radar and terrain relative navigation, it scanned the surface in real time, comparing what it saw to preloaded maps to determine exactly where it was. Then came the retro rockets. A descent stage ignited engines to slow the vehicle further. But even that was not enough to land the rover safely without risk. So NASA introduced one of the most unusual solutions ever attempted in spaceflight, the sky crane. Instead of landing the rover directly, the descent stage hovered above the surface and lowered the rover on cables. This avoided the problem of rocket exhaust kicking up debris or destabilizing the landing site. The rover touched down gently while suspended, and then, in the final seconds, the cables were cut and the descent stage flew away to crash at a safe distance. From start to finish, the entire sequence took about 7 minutes. 7 minutes of continuous, irreversible decision-making. 7 minutes where nothing could be paused, corrected, or retried, and most importantly, 7 minutes that were entirely autonomous. Because Mars is too far away for real-time control. By the time engineers at NASA received confirmation that atmospheric entry had begun, the landing was already over. The rover had either landed successfully or it had been destroyed. There is no in-between. Now consider the scale of what was just accomplished. Perseverance weighs about 1 metric ton. Everything you just heard, the heat shield, the parachute, the retro rockets, the sky crane, was designed to land a machine roughly the size of a small car. A human mission is something else entirely. A crewed Mars lander is not just carrying people, it is carrying their entire survival system. Habitats, life support, oxygen reserves, water, food, tools, scientific equipment, spare parts, and the ascent vehicle needed to leave the surface again. You're not landing 1 ton, you're landing 20, possibly 40, And here is where the physics stops cooperating. Engineering does not scale linearly. You cannot simply take the system used for Perseverance and make everything 20 times larger. A parachute that works at 1 ton does not work at 20. A heat shield that survives at one scale behaves differently at another. A descent engine that is sufficient for a rover introduces entirely new risks when scaled up for human payloads. Every system begins to interact differently under increased mass, and those interactions are not fully predictable. Take parachutes again. To slow a 20 to 40 ton vehicle, you would need a parachute far larger than anything ever tested at supersonic speeds. Deploying such a structure in Mars's atmosphere risks catastrophic failure. The forces could shred it instantly, and even if it survived, it might not provide enough drag to matter. So what if you remove parachutes entirely and rely on rockets? That creates another problem: fuel. To slow a massive spacecraft from hypersonic speeds using only retro rockets requires enormous amounts of propellant, and that propellant has mass, which means you need more fuel to land the fuel, which increases the total mass, which requires even more fuel. This feedback loop escalates quickly and becomes one of the defining constraints of the mission. There are proposed solutions. None are simple, none are fully proven. Inflatable aerodynamic decelerators are one option, massive deployable structures that increase drag area before the parachute phase. Supersonic retropropulsion is another, where rockets fire while the vehicle is still travelling faster than the speed of sound, augmenting atmospheric braking. Companies like SpaceX have demonstrated aspects of this technique on Earth, but Mars presents a different environment entirely. The atmosphere is thinner, the margins are tighter, and the cost of failure is absolute. The core issue is not that these technologies are impossible. It is that none of them have been tested at the scale required for a human landing on Mars. Every successful mission, Viking, Pathfinder, Spirit, Opportunity, Phoenix, Curiosity, Insight, Perseverance, has validated pieces of the puzzle. But the leap from 1 ton to 20 or 40 is not incremental. It is a discontinuity. It requires new systems, new materials, new testing methods, and validation in an environment that cannot be fully replicated on Earth. And this is where the problem becomes unavoidable. You cannot fully test a Mars landing system on Earth because the atmosphere is wrong. You cannot easily test it incrementally on Mars because each mission is expensive, infrequent, and high risk. And you cannot assume that success at a smaller scale guarantees success at a larger one, because Mars has a long history of punishing exactly that kind of assumption. So what you're left with is this. The most critical phase of the mission depends on systems that have not yet been built, operating at scales that have not yet been tested, in an environment that cannot be fully simulated. 7 minutes where everything must work perfectly. 7 minutes where there is no intervention, no correction, and no second chance. Because on Mars, failure is not something you recover from. It is something you arrive at. Part 12. Mars punishes small mistakes. There is a pattern in the history of Mars missions that is easy to miss if you only look at the headlines. When we think about space failures, we imagine explosions, dramatic system breakdowns, or unknown physics pushing technology beyond its limits. But Mars doesn't usually destroy missions in spectacular ways. It does something quieter and far more unsettling. It takes small, ordinary mistakes and stretches them until they become irreversible. Roughly half of all missions sent to Mars have failed. That statistic alone is alarming, especially when compared to the much higher success rates we see in Earth orbit, or even with lunar missions. But the deeper story isn't just the failure rate, it's the type of failures. Many of them weren't caused by impossible engineering challenges or mysterious phenomena. They were caused by simple, almost mundane errors, the kind that, on Earth, would be caught, corrected, and forgotten. Take the Mars Climate Orbiter. It launched successfully, travelled millions of kilometres through space, and reached Mars right on schedule. From a distance, it looked like a textbook mission. But as it approached the planet, something subtle went wrong. One engineering team had been using metric units, while another used imperial units. That mismatch slipped through the system. No one caught it in time. The result was a trajectory miscalculation that sent the spacecraft too low into the Martian atmosphere. Instead of entering orbit, it was lost, likely burned up or thrown off course beyond recovery. Years of work, hundreds of millions of dollars, and a fully functional spacecraft were erased by a unit conversion error. Not a failure of technology, a failure of coordination. Then there's Beagle 2, a mission that tells an even stranger story. For years, it was assumed to have crashed during landing. That assumption made sense. Mars landings are notoriously difficult, but later, high-resolution images revealed something unexpected. The lander had actually reached the surface intact. It survived the descent. It did everything it was supposed to do, except one small thing. Its solar panels didn't fully deploy. That mattered because the panels also exposed the communication antenna. With one panel stuck, the antenna remained blocked. The spacecraft was alive, sitting on the surface of Mars, but it couldn't send a signal. A minor mechanical issue, something that could likely be fixed in hours on Earth, turned into a permanent silence. The mission didn't fail dramatically. It simply stopped existing from our perspective. This is the pattern Mars repeats. It doesn't need catastrophic failures to end missions. It only needs small ones. The environment does the rest. The reason for this comes down to a single factor that shapes everything about Mars missions: distance. Mars is not just far away, it is functionally isolated. Even at its closest, it is minutes away at the speed of light. That means every message sent from Earth takes time to arrive, and every response takes just as long to come back. At best, you're dealing with an 8-minute round trip. At worst, nearly 50 minutes. That delay changes everything. On Earth or in low orbit, problems can be addressed almost instantly. Engineers can respond in real time, guide astronauts through fixes, or adjust systems as events unfold. But on Mars, by the time Mission Control even becomes aware of a problem, the situation may already be beyond recovery. There is no real-time intervention, no immediate troubleshooting. The spacecraft or the crew must handle the issue alone, in the moment, with whatever tools and knowledge they already have. This is why Mars missions rely so heavily on autonomy. Systems must be designed to detect problems, interpret them, and respond without waiting for human input from Earth. But autonomy has limits. It can only handle situations that were anticipated in advance. When something unexpected happens, and in complex systems something always does, the margin for error disappears quickly. For robotic missions, this means the difference between success and silence. For human missions, it raises the stakes to an entirely different level. Because now, the system that must not fail is not just a machine. It's a life support environment. Every component is part of a closed loop. Air, water, temperature, pressure. Each system depends on the others. A small failure doesn't stay small for long. It spreads. A minor leak in a seal might lead to pressure loss. A faulty sensor might misread oxygen levels. A glitch in software might trigger the wrong response from a critical subsystem. On Earth, these are manageable issues. Engineers can step in. Parts can be replaced. Systems can be shut down and restarted. On Mars, there is no outside help. There is no backup team walking into the room. There is only the crew, the equipment they brought with them, and the time they have before the situation escalates. And the crew themselves are not operating at full capacity. They're dealing with prolonged exposure to radiation, including high-energy particles that may affect brain function over time. Research suggests these particles can impact memory, decision-making, and behavior. The exact effects on humans are still uncertain, but the possibility is there, and it matters when every decision counts. They are dealing with psychological stress that has no real equivalent on Earth. Isolation, confinement, delayed communication, and the knowledge that rescue is impossible create a constant background pressure. Even in controlled simulations, tension builds over time. Small disagreements can grow, fatigue accumulates, focus slips. They're also dealing with an environment where routine tasks are inherently risky. Every excursion outside the habitat requires a suit. Every surface is coated in fine, reactive dust. Equipment wears down. Systems degrade. Nothing is stable for long. In that context, small errors are not rare. They are inevitable. And on Mars, small errors don't stay small. Imagine a scenario deep into the mission, month 14, right in the middle of the surface stay. The crew is settled into routines. Systems have been running for over a year. Wear and tear is beginning to show. Then something minor happens. A valve doesn't close perfectly. A sensor starts returning inconsistent readings. It's not immediately alarming, just a small anomaly. On Earth, this would trigger a series of checks. Engineers would analyze the data, run diagnostics, and schedule a repair. On Mars, the crew has to make a decision quickly. Do they intervene immediately? Do they wait for more data? Do they risk shutting down a system that might still be functioning? Every option carries risk. If they act too soon, they might disrupt a system unnecessarily. If they wait too long, the problem might escalate. And by the time mission control weighs in, minutes or tens of minutes later, the situation may have already changed. This is how small issues become critical failures. Not because they are inherently dangerous, but because the environment gives you no margin to manage them safely. Mars amplifies everything. Time delays stretched decisions. Isolation removes backup. Complexity creates hidden dependencies. And the environment itself ensures that recovery is never simple. That is the real pattern. Not just that missions fail, but how they fail. Mars does not need to overwhelm you with force. It only needs you to make a small mistake at the wrong time in the wrong place, and then it does the rest. Part 13. You're completely alone. Somewhere in the middle of the 9-month transit from Earth to Mars, long after the excitement of launch has faded, and before the reality of landing has begun, the mission settles into a kind of quiet routine. The spacecraft becomes a closed world. Every system is running. Every checklist is familiar. Every movement deliberate. And it is in that controlled, predictable environment that something small appears. A crew member develops a headache. At first, it doesn't stand out. Spaceflight comes with a range of minor physiological effects. Fluid shifts toward the head, disrupted sleep cycles, changes in intracranial pressure. Headaches are not unusual, but this one lingers. 2 days pass, the pain remains. It doesn't respond to the standard medication available in the onboard medical kit. It isn't debilitating, but it isn't fading either. It sits there, persistent, just outside the boundary of what feels normal. On Earth, this would trigger an immediate and familiar process. You would speak to a doctor. You would describe the symptoms. You would answer follow-up questions in real time. Within minutes, a pattern would begin to form. A diagnosis might not be immediate, but a direction would be clear. On a Mars mission, that process unfolds differently. The flight surgeon on Earth reviews the incoming biometric data from the spacecraft. Heart rate, blood pressure, sleep logs, activity levels, anything that might provide context. They compose a message asking for more detail. When did the headache begin? Is there any visual disturbance? Does the pain worsen with movement? Has there been any change in routine, hydration, or stress levels? The message is sent. It takes 12 minutes to arrive. The crew member reads it carefully, thinking through each question, and dictates a response. Another 12 minutes pass as that reply travels back across the void. The flight surgeon receives it, reviews the answers, and consults with colleagues, perhaps a neurologist, perhaps a specialist in space medicine. They discuss possibilities, weighing each one against the limitations of the environment. No imaging equipment beyond basic tools, no surgical capability, limited medication. They formulate a follow-up question and a preliminary assessment. They send it back. Another 12 minutes. By the time the crew member receives that response, nearly an hour has passed since the first message was sent. And this is the best-case scenario. Everything is working. The communication system is stable. There are no interruptions, no delays beyond the unavoidable speed of light. Everyone is attentive. The issue is relatively minor, a headache, not a cascading system failure. Even then, nearly an hour separates question and answer. That delay is not just inconvenient. It fundamentally reshapes what it means to have support. Every previous crewed space mission has operated under a simple, powerful assumption. Earth is always there, in real time. During the Apollo era, astronauts orbiting the Moon could describe a problem and receive guidance within seconds. The communication delay was barely noticeable, just enough to remind you of the distance, but not enough to disrupt the flow of conversation. When crises emerged, as they did during Apollo 13, the crew was never truly alone. Engineers on the ground worked alongside them in continuous dialogue, analysing, adapting, guiding every step. On the International Space Station, that connection is even stronger. Astronauts can speak directly with flight surgeons, engineers, and mission control in real time. A medical concern becomes a conversation. A technical issue becomes a collaborative problem-solving session. The structure of the mission assumes that expertise on Earth is always accessible. That assumption has shaped everything about human spaceflight. It defines how crews are trained, how responsibilities are divided, how emergencies are handled. It allows for specialization. Astronauts do not need to be experts in every field, because experts are always available. A Mars mission removes that assumption entirely. There is no real-time communication. There is no immediate back and forth. There is no conversation in the way we understand it. There are only messages, separated by long intervals of silence. A crew on the International Space Station calls a doctor. A crew on Mars sends a message and waits. The consequences of that shift extend far beyond emergencies. They reach into every aspect of the mission. Routine maintenance, system diagnostics, scientific experiments, these are no longer guided step by teams on Earth. The crew must interpret data, make decisions and act independently. If something unexpected occurs, there is no immediate clarification, no quick question, no instant reassurance. They must decide. This transforms the role of the crew in a fundamental way. They are no longer just operators. They are the mission's entire knowledge base. Each individual must carry within them the skills of multiple disciplines: medicine, engineering, geology, biology, systems management. On Earth, these roles are distributed across teams of specialists. On Mars, they are compressed into a handful of people. And it is not enough to possess that knowledge in theory. It must be applied correctly, under pressure, in real time. A medical issue arises, you are the doctor. A mechanical anomaly appears, you are the engineer. A systems failure unfolds, you are the analyst and the decision maker. There is no higher authority to defer to in the moment, no escalation path that leads to immediate intervention. The crew is the final layer of decision-making, and they must function this way continuously for the entire duration of the mission. There is also a second layer to this isolation, one that is less technical, but just as profound. Real-time communication is not just a tool, it is a psychological anchor. On the International Space Station, astronauts are in constant contact with Earth. They hear voices, they share moments, they exist within a continuous stream of interaction that connects them to a larger human context. Even in orbit, they remain part of a living network. That connection matters. It reinforces a sense of belonging. It provides emotional grounding. It allows for immediate support in moments of stress or uncertainty. On a Mars mission, that connection becomes fragmented. Communication is delayed. Conversations stretch across hours. Emotional exchanges lose their immediacy. A question takes minutes to reach Earth. A response takes minutes to return. The rhythm of interaction is broken. The crew is no longer part of a real-time dialogue. They are part of an asynchronous exchange. It begins to feel less like a conversation and more like correspondence. Letters, sent across vast distances, replies that arrive long after the moment has passed. This changes the psychological landscape of the mission in subtle but significant ways. The crew begins to experience themselves not as an extension of Earth, but as something separate, a small, self-contained group operating independently in a hostile environment. They are not just far from Earth, they are disconnected from it. Earth becomes distant not only in space, but in time. Its responses are delayed, its presence is abstract, its support, while still real, is no longer immediate. The crew becomes, in a meaningful sense, their own system, a small autonomous unit responsible for its own survival. And that autonomy carries weight, because autonomy means responsibility. The crew cannot wait for permission in time-critical situations. They cannot delay action while awaiting advice that may arrive too late. They must act based on their own judgment, in the moment, with incomplete information. Every decision matters. A misinterpretation of data, a delayed response, a choice made under fatigue or stress. On Earth, these are manageable errors. There are buffers, redundancies, second opinions. On Mars, there is no such margin. The environment does not forgive hesitation. It does not allow for easy correction. A wrong decision is not an inconvenience. It is a cascade. And the cascade does not stop on its own. This is the reality that sits beneath the idea of a Mars mission. It is not just a journey across space. It is a transition into a completely different operational reality. A place where time is stretched, communication is delayed, and responsibility is absolute. Where the crew must carry not only the tools for survival, but the judgment to use them correctly, every time. Because there is no one else who can, and no one who can get there in time if they cannot. Part 14. The 2.7-year trap. In 2010, the European Space Agency, working alongside Russia's Institute of Biomedical Problems, launched one of the most ambitious psychological experiments ever attempted for space exploration. It was called Mars 500, and its premise was simple on the surface but profound in implication. If we cannot yet send humans to Mars, we can at least try to understand what it does to the human mind. 6 volunteers, 3 Russian, 1 French, 1 Chinese and 1 Italian Colombian, entered a sealed mock spacecraft facility in Moscow. The doors closed behind them, and for the next 520 days, they lived inside a simulation of a Mars mission. There was no real space outside the walls, no vacuum, no radiation, no alien landscape. What they experienced instead was something more controlled but still deeply revealing. Confinement, isolation, delayed communication, and the slow passage of time in a sealed environment. The facility was designed to mimic the structure of a Mars mission: transit to Mars, a simulated landing phase, and the long return journey. Communication with the outside world was artificially delayed to reflect the real signal lag between Earth and Mars. Supplies were limited. The environment was repetitive and unchanging. It was in many ways the closest approximation humanity had ever created of a Mars mission without actually leaving Earth. The results were, at first glance, reassuring. The crew did not collapse under the psychological pressure in the way some researchers had feared. There were no dramatic breakdowns, no irreversible conflicts, no mission-ending emotional crises. Depression levels remained low. The group maintained functional relationships. They completed their assigned tasks. From a distance, it looked like a success story, a proof of concept that humans could endure long-duration isolation without falling apart. But the deeper findings told a more complicated story. The most striking pattern was not internal conflict within the crew, but tension between the crew and mission control. Even in a simulated environment, where both sides understood the artificial nature of the setup, communication delays began to reshape relationships. Messages from mission control, delayed and stripped of immediate context, were sometimes perceived as blunt or overly directive. Without real-time conversation to soften tone or clarify intent, small misunderstandings began to accumulate. Over time, these misunderstandings created friction, not explosive, but persistent. Inside the crew, something else was happening. Each individual began to develop their own way of coping with the isolation. At first, these strategies were subtle, differences in how they structured their day, how they managed stress, how they interacted with others. But as the mission progressed, these coping mechanisms diverged more significantly. Researchers describe this phenomenon as asynchronous adaptation. In simple terms, it meant that the crew members were no longer moving through the psychological phases of the mission together. One person might be in a period of high motivation, while another was experiencing fatigue or withdrawal. One might seek social interaction, while another preferred isolation. This misalignment created quiet tension, not open conflict, but a kind of psychological drift. The crew was still functioning as a unit, but internally they were no longer synchronized. By the later stages of the experiment, other patterns emerged. Sleep cycles began to degrade. Without natural environmental cues, circadian rhythms drifted. Some crew members adopted irregular sleep schedules, which further desynchronized the group dynamic. Physical activity also declined. Despite having the equipment and the knowledge to maintain fitness, motivation decreased over time. Exercise routines became less consistent, then sporadic, and in some cases nearly absent. None of these effects were catastrophic on their own, but together they painted a picture that was far more nuanced than the initial headline suggested. The crew survived the simulation. They did not break, but they changed in ways that mattered. And then there was the most important limitation of all. At every moment of those 520 days, the participants knew something that cannot be replicated in a real mission. They knew they could leave. The door was always there. They had committed to the experiment, and by all accounts, they took that commitment seriously. But the knowledge of an escape route, even one they never intended to use, changes the psychological landscape. It creates a safety net that exists beneath every stressful moment. No matter how difficult things become, there is a boundary between the simulation and reality that can be crossed. A real Mars mission does not have that boundary. There is no door, there is no exit, there is no scenario in which the crew decides they have had enough and returns to Earth early. Once the spacecraft departs on its trajectory, the mission is locked in by orbital mechanics. The crew is committed for the full duration, whether conditions remain stable or begin to degrade. This difference between simulated isolation and irreversible isolation is difficult to quantify, but it is critical. Mars 500 showed us how people behave when they choose to stay. It did not show us how people behave when they cannot leave. A similar set of insights came from another series of experiments known as HI-Cs, the Hawaii Space Exploration Analog and Simulation Program. Conducted on the slopes of Mauna Loa, these missions place small crews inside a dome designed to simulate the conditions of a Mars surface habitat. The participants lived in isolation for periods ranging from 4 months to a year, conducting mock spacewalks, managing limited resources, and communicating with delayed messages. Like Mars 500, the HICAS missions revealed a consistent psychological arc. The beginning was marked by enthusiasm. A sense of purpose, novelty, and excitement carried the crew through the early phase. Everything was new. Every task felt meaningful. The mission had momentum. Then came the middle phase. This was where friction began to emerge. The novelty wore off. The environment became repetitive. Small irritations, differences in habits, communication styles, personal preferences started to matter more. Nothing dramatic, but enough to create tension beneath the surface. Finally, the missions entered what researchers described as the asynchronous coping phase. Much like in Mars 500, crew members began to diverge in how they handled stress. Some withdrew, others became more assertive. Emotional states no longer aligned. The group dynamic became more complex, less predictable. Again, the missions were successful. The crews completed their objectives. They demonstrated resilience, adaptability, and professionalism. But again, there was an escape hatch. The dome was on Earth. If something went seriously wrong, medical emergency, equipment failure, psychological breakdown, the crew could be evacuated within hours. That knowledge, even if never acted upon, changes the experience. It softens the edges of isolation. It introduces the possibility of relief. A real Mars mission removes that possibility entirely, and this is where time becomes the most important factor of all. A Mars mission is not just long, it is inescapably long. Approximately 2.7 years. That number is easy to say, but difficult to fully grasp. It is not a sprint. It is not even a marathon. It is closer to a sustained state of existence. Nearly 3 years of waking up in the same confined environment, surrounded by the same small group of people, with no variation in setting and no possibility of stepping outside without life-threatening consequences. During the transit phases, the crew is confined to a spacecraft, hundreds of cubic meters of pressurized space, carrying everything they need to survive. On the surface, the habitat may be slightly larger, but the constraints remain. Every movement is bounded, every resource is limited, and outside those walls is an environment that does not tolerate error. Stepping outside without protection is fatal. The atmosphere is unbreathable. The pressure is too low to sustain human physiology. The temperature fluctuates beyond survivable limits. Every excursion requires planning, equipment, and risk. At the same time, Earth is not just far away, it is unreachable in any practical sense. Communication is delayed. Rescue is impossible. The sky above is not familiar. Earth appears as a distant point of light, not a place you can return to on a whim. And then there is the constraint that defines the entire mission timeline: orbital mechanics. The crew cannot leave Mars whenever they choose. The return window opens only when Earth and Mars align correctly in their orbits. That alignment occurs approximately every 26 months. Miss the window, and you wait. So when the crew lands, they are not just beginning a mission. They are entering a period of enforced presence, roughly 14 to 15 months on the surface, regardless of how they feel, regardless of what happens. If something goes wrong, they cannot accelerate the timeline, they cannot leave early, they wait. Psychological research on long-duration confinement suggests that the greatest challenge is not a single catastrophic event, but the accumulation of small stressors over time. It is not one argument that breaks a crew. It is 100 small disagreements that never fully resolve. It is not one bad day. It is the slow erosion of novelty, the repetition of routine, the absence of variation. It is the sound of someone chewing in a confined space day after day. The difference in how two people approach a task. The tone of a message from mission control that feels slightly off, but cannot be clarified in real time. The memory of home that becomes less vivid with each passing month. Individually, these things are insignificant. Together, they define the experience. On Earth, stress can be relieved. You can leave the room, go outside, talk to someone new, change your environment. On Mars, there is no outside. There is only the habitat, the spacecraft, and the surface, a surface that cannot be experienced without layers of protection and constant awareness of risk. The stress does not dissipate, it accumulates, and it accumulates in an environment where every other challenge is present at the same time. Radiation exposure continues day after day, potentially affecting physical health and cognitive function. The body adapts to reduce gravity, but not without consequences. Sleep cycles drift. Physical conditioning requires constant effort to maintain. Systems require maintenance. Experiments require attention. The mission does not pause for psychological recovery. Everything happens at once. The 2.7-year duration is not just a timeline. It is the structure that holds every other challenge in place. It is the container within which radiation accumulates, systems degrade, relationships evolve, and decisions are made. It is not simply added to the mission. It is the mission. And everything that happens, every success, every failure, every moment of resilience or doubt happens inside it, with no way to step outside and reset. That is what makes a Mars mission fundamentally different from anything humanity has attempted before. It is not just a journey through space, it is a sustained confrontation with time, isolation, and the limits of human endurance, carried out in an environment that offers no escape and no margin for error. Part 15. The Final Realization. Let us go back to the beginning, because everything about a Mars mission becomes clearer when you stop treating it as a story and start treating it as a set of constraints that all point in the same direction. A single Mars mission exceeds NASA's career radiation limit. That fact is often mentioned in passing, as if it were just another technical hurdle, but it is actually something far more fundamental. It is a summary of intent, a compressed statement of what the mission truly is beneath the language of exploration and discovery. NASA established a career radiation limit for a simple reason that becomes difficult to ignore once you sit with it long enough. Space radiation is not abstract. It is cumulative damage. It is the slow accumulation of cellular risk, of DNA disruption, of long-term probability shifting against the human body. The limit exists because, beyond a certain threshold, the probability of serious health consequences becomes too high to justify exposure. Cancer risks increase, cardiovascular risks rise, neurological impacts become more likely. The agency did not set that limit casually. It was the result of decades of data, analysis, and cautious interpretation of what space does to biology over time. And yet, the first mission to Mars will knowingly push astronauts past that limit as a baseline requirement of participation, not as an accident, not as an anomaly, as the mission profile itself. That single fact, standing alone, already reframes everything. But it becomes even more significant when placed alongside the rest of the architecture of a Mars mission. The atmosphere that kills unprotected humans in seconds, the soil enriched with perchlораtes at levels that interfere with thyroid function and contaminate enclosed habitats through dust transport. The global dust storms capable of enveloping the planet and cutting off solar power for weeks or months. The landing problem that still represents one of the highest risk phases of any robotic or crewed mission ever attempted. The communication delay that turns every interaction with Earth into a slow, asynchronous exchange rather than real-time support. The psychological burden of near 3-year confinement with no evacuation option. The orbital mechanics that physically prevent return during most of the surface stay, and the potential cognitive impacts of sustained radiation exposure on the very people responsible for managing all of these risks simultaneously. Each of these constraints is severe on its own. Together they form something that has no real precedent in human experience. It is tempting to compare Mars missions to other extreme environments, but the comparison always breaks down under scrutiny. Mount Everest, for example, is dangerous, but it is also fundamentally accessible. Climbers can be rescued. Descents happen within hours or days. The environment is hostile, but it is not absolute. Antarctica is isolated, but not irreversibly so. People overwinter there, but evacuation remains possible under the right conditions. Even the most extreme Antarctic expeditions occur within a system that still has an external safety net. The Apollo missions, often invoked as the pinnacle of human exploration, were extraordinary precisely because of their constraints, but they were brief. Days, not years. And crucially, they operated within a regime where Earth was always close enough for immediate intervention if physics allowed it. When Apollo 13 suffered a catastrophic failure, rescue was difficult, but it was not impossible. The trajectory still allowed a return path. The system still permitted intervention from Earth-based teams working in real time. A Mars mission removes that category of possibility entirely. What remains is something fundamentally new. A closed, self-contained human system operating at the edge of engineering capability on a planet that has transitioned from potentially habitable to definitively hostile over billions of years without any capacity for external rescue or real-time correction. A small group of humans functioning as both operators and system-critical infrastructure for their own survival. It is not just exploration. It is sustained autonomy under permanent constraint. Every element of the mission exists simultaneously, not sequentially. Radiation exposure accumulates while psychological stress increases. Systems degrade while dust storms reduce power margins. Scientific objectives continue while communication delays prevent immediate clarification. Maintenance tasks overlap with emergency preparedness. Nothing pauses, nothing resets. The crew lives inside a continuously active stack of risks that cannot be separated from one another. Now consider what this means in practice. A medical anomaly occurs during surface operations. A crew member reports symptoms that are unclear but persistent. On Earth, this would be a straightforward diagnostic conversation. A doctor would ask questions in real time, adjust hypotheses based on immediate feedback, request additional tests, and refine understanding dynamically. On Mars, that process is fragmented. A message is sent. Minutes pass before it arrives. Minutes pass again before a response is formulated. More minutes pass before clarification is received. In that time, the condition has already evolved. The situation has already shifted. The feedback loop is too slow to stabilize rapidly changing conditions. This is not just a medical issue. It is a structural feature of the entire mission. Every decision exists inside a delay loop that fundamentally alters how support works. Earth is no longer a real-time partner in decision-making. It becomes an asynchronous advisor whose input arrives after the moment of action has already passed. That shift forces a deeper transformation in crew identity. The astronauts are no longer operators supported by mission control. They become the highest level of authority within the system simply because no higher authority can act quickly enough to matter. They are in effect the entire decision-making structure of the mission compressed into a small group of individuals. That carries implications that extend beyond technical skill. It demands psychological resilience under conditions that do not reset. It demands medical competence, engineering judgment, systems thinking, and conflict resolution capacity, all embedded within the same individuals. On Earth, these responsibilities are distributed across entire organizations. On Mars, they converge. And they converge inside an environment that does not forgive hesitation. At the same time, psychological research on long-duration isolation suggests that the most significant challenges are not singular dramatic events, but the accumulation of minor frictions over time. A disagreement that is never fully resolved, a habit that becomes irritating under repetition, a tone in a delayed message that is interpreted differently than intended, a routine that becomes monotonous after hundreds of repetitions, a sense of distance from Earth that grows not suddenly but gradually, like a slow shift in perspective. Individually, none of these factors are mission-threatening. Together they form the psychological texture of isolation. And unlike Earth-based environments, there is no relief valve, no change of scenery, no escape into external social networks, no real-time emotional recalibration through immediate conversation. Even communication itself becomes structurally different. Instead of dialogue, there is correspondence. Instead of conversation, there is exchange. The emotional continuity of shared presence is replaced by delayed response cycles that cannot support the same psychological feedback loops humans rely on in daily life. Now layer that onto the physical environment. Radiation continues to accumulate in the background, quietly influencing long-term health risks and potentially cognitive function. Reduced gravity alters musculoskeletal systems in ways that require constant counteraction. Environmental hazards require procedural vigilance at all times. Maintenance demands are continuous. Scientific operations are ongoing. There is no downtime in the traditional sense because the system cannot afford it. Everything is active, everything is ongoing, everything is constrained. This is where the timeline becomes critical. A Mars mission is not simply long. It is structurally fixed at approximately 2.7 years. That duration is dictated not by human preference, but by orbital mechanics. Earth and Mars align in cycles that determine when transfer windows open and close. Once the crew departs Earth, They enter a trajectory that does not permit arbitrary return. Once they arrive on Mars, they are bound by planetary motion to remain until the next viable departure window opens, which may be more than a year after landing. There is no flexibility in that system. There is only timing. This means that every challenge, every risk, every operational demand exists inside a fixed container of time that cannot be shortened. Stress does not lead to early termination. Fatigue does not lead to evacuation. Psychological strain does not trigger return. Everything must be managed within the duration of the mission itself, and that duration is long enough for every minor issue to compound. A Mars mission is therefore not a sequence of events. It is an extended state of exposure, a continuous condition in which multiple stressors interact without relief, and the crew must operate within that condition while maintaining the systems that keep them alive. That is the essential reality beneath all the engineering and planning. Finally, when all of this is stripped down to its core, what remains is not a story of conquest or expansion, but something more restrained and more profound. A small group of human beings placed in an environment that has been hostile to life for billions of years, surviving through a combination of technology, discipline, and constant adaptation, with no external rescue available and no ability to reset the conditions around them. Mars will not change during this process. It will remain what it has always been, a planet that lost its habitability long ago and has retained the record of that loss in its atmosphere, its soil, and its silence. The variable in the equation is not Mars, it is the human presence placed upon it, and when those first crews eventually return, if they return, they will not simply bring back data or samples or engineering lessons. They will bring back something less tangible but more important. A lived understanding of what it means for human cognition, physiology, and psychology to persist in a state of total isolation from Earth while embedded in a system that is actively hostile to survival. The question that remains, after all the engineering is accounted for, is not whether the mission can reach Mars. It almost certainly can. It is not even whether humans can survive there for a limited period. That is plausible within known constraints. The question is what it does to the humans who attempt it, because Mars will remain unchanged, but the people who go there will not,